pleasure to introduce Dina Goldin, who's an assistant professor at the University of Connecticut and has an appointment at Brown University also. She got her PhD from Brown University under somebody named Paris Kanelakis, whom I don't know, but I'm sure.
Database guy.
I see.
There's no ACM. PhD stands for philosophy. So once in a while, we may want to step back and ask some of the more philosophical questions about the assumptions that underlie our work. By I mean computer science, which is what my degree is in. And even though these questions, of course, are something that may interest people from other fields, mathematicians, electrical engineers, philosophers. So the questions are, what is computation and how do we model it? Okay. And these are not new questions. These are very old questions. And certain answers to these questions are something that all computer scientists learn in our undergraduate theory of computation courses. And these answers are what I call shared wisdom. So the shared wisdom of computer scientists regarding these questions are that computation is a finite transformation of input to output. And input itself is a finite size token such as a string or natural number or rational number. And the computation proceeds in the context of a closed system. All input is available at the start, all output is generated at the end. Okay? So the behavior of these computational devices is the behavior of functions, transforming input data to output data. And one more thing that we'll learn in the theory of computation courses regarding this notion of computation is what's known as the Church-Turing thesis, that Turing machines capture this notion of computation, which we call algorithmic notion of computation. Okay? So I call this the mathematical worldview of computation. That all computable problems are function-based. To solve a problem means to find a function that takes your input and computes the output. Okay? Now, this mathematical worldview, as I said, is old. In fact, it is even older than computer science itself. Okay? Theory of computation was first a part of mathematics. So in 1958, Martin Davis published a book, Computability and Solvability, that became one of the first textbooks in this topic for people that became the leaders in the theory of computation community. And it said right at the beginning of the book, the theory of computability, non-computability, is the theory of recursive functions. And that the notion of TM is central here because it represents the computation of all recursive functions. Okay? So let's go back almost a half a century, and a year ago, SIGACT News pointed out that of all undergraduate computer science subjects, theoretical computer science has changed the least over the decades. Okay? And this is reflected in our textbooks that we use in theory of computation. So I will quote from the one that I'm using in my course this semester, and this is typical of other books as well. A Turing machine can do anything that a computer can do. Okay, so there's this, Turing machines remain central, and the way they compute remains at the center of how we understand computation. Okay, now there are problems with this worldview. Okay, so because what real computers do, they run operating systems and they run applications such as word processors, and it's acknowledged that real programs like these work by receiving an unbounded amount of input over time, and they never finish their tasks, and Turing machines do not model such ongoing computation well. So this is what I call the operating system conundrum, where somebody who studies computer science theory would say, well, if a computation doesn't terminate, the theory tells us it's useless. But aren't operating systems useful even though they don't stop computing? Okay, so this conundrum could be swept under the rug before, but at this point it's really time to rethink what computers do. Okay, so what is it that computers really do? Well, computation, so every time something here comes up, you should contrast it with this one and understand that these two are different points of view. They're incompatible, basically. That computation is an ongoing process which performs a task or delivers a service. Okay. And the input is a stream of tokens, such as requests, percepts, messages, that is generated dynamically. So the word dynamic is a key word that means that the input is not generated until it's needed and not necessarily before the computation starts. Okay. And the context here is that of an open system where later inputs depend on earlier outputs and vice versa. So there's concurrent exchange of information between a system and its environment. Okay? So the behavior that we're discussing here is not anything exotic. This is the typical behavior of processes, of components, of control devices, reactive systems, and intelligent agents. So I'm not really describing anything new. What I'm doing, what's new though, is that I'm actually reconceptualizing computation to be more accountable to this type of behavior. So, and this work that I'm about to present is motivated by a conjecture made by Peter Wegener in his controversial CACM article in 1997, that interaction, which means this kind of computation, is more powerful than algorithms, meaning this kind of computation. That you can actually compare them somehow and actually conclude that this kind of computation is more expressive. Okay? So the way things work in theoretical computer science, if you claim greater expressiveness, you have to actually present a problem that can be expressed in one formalism but not another. Otherwise, you can't say that it's more expressive. So let me present you one such problem. And the problem is driving home from work. Okay? So the input to this problem is a description of the world. Some kind of a static map that completely describes everything that the car will need to, that the problem will need to know in order to compute, to compute the driving path. Okay? So this is your work, and this is the home, and this is everything you need to know about the road. And then there's a very intelligent search algorithm whose output are just these two time series data sequences. The one tells you how to turn the wheel. The other tells you how much to press on the gas and the brake. And between them, if you were to feed these to a machine, to a car, the way you feed these tapes to play a piano to tell it how to strike the keys, so it will actually be able to get you from your work to your house by executing these series of signals for the wheel and the brake. So this is standard for classic AI search and planning problems. Okay? But but remember, we're not talking about driving in the real world. Okay? So we want that algorithm to get the car into your driveway without running over anyone along the way. Okay? So in the real world environment, the output depends on every grain of sand in the road. This is chaotic behavior. If you miscalculated on your map, if on your map you did not properly indicate the position of one grain of sand in the road, then far enough down, your car is going to end up in your living room window instead of your driveway. Okay? So this map needs to be awfully detailed. But things get even worse because the domain is dynamic. So the position of that grain of sand and on everything else will change as after the car starts driving. And so therefore, the output will depend on weather conditions and on other drivers as pedestrians that will be taking place after the car will start driving. And at this point, you really have to give up and say we cannot be expected to be able to predict things like pedestrian movement ahead of time. Philosophers have been working on this problem for 1,000 years. Is there predestination? Is there no predestination? Who are we, engineers and computer scientists, to tell them that we can definitely compute it? We have to assume we can't. Okay? Well, never, so even though we have been forced to give up and say we can't do it, the problem is doable. I mean, you know, there is research in autonomous vehicles going on in very respectable universities, and they wouldn't be doing it if the problem wasn't doable. So what's the trick? Well, the trick is that you have to reinterpret what you mean by a problem. Okay? So this problem is solvable but interactively, where interaction is the right-hand side of the earlier table. Okay? So in the interactive paradigm, the input is not a single description given to the computation ahead of time. It is an ongoing stream of video camera images, in this case, that is gathered as the car is driving. So here comes the input into the camera. The car recomputes, adjusts the wheel and the gas brake, and as a result, it drives what it needs to drive, and its output is that very same time series sequence that we wanted from the beginning. But it is generated as we are driving rather than ahead of time. So this is the way control systems work and the way online computation works, but it represents a paradigm shift in our conceptualization of what it means to compute and what is a problem, what is a solvable problem. So, you know, whereas before the problem of driving from home from work was not a solvable problem, now it is a solvable problem. Okay? So at this point, I hopefully have motivated my talk. And I will now move on to actually working on the proof of Peter Wagner's conjecture. And I will start by presenting a model of interactive computation. That model is based on a standard Turing machine model. So Turing machine, I already mentioned what they are before. This particular one has three tapes: the input tape, the work tape, and the output tape. And it also has an internal state, one of the finite set of states. And so its configuration consists of the current state, the current contents of these three tapes, and the current position of the reading heads on these three tapes. And the computation of this machine is defined in the standard way as a sequence of transitions from between configurations that starts so that the computation starts in the initial configuration and moves on to the halting configuration. Okay, so this is really nothing new. So what's new now is how we're going to extend these computations. We're going to extend in two ways. First, we're going to change the input semantics to dynamic streams, meaning that our input is a stream of strings. Here's the first string, input 1. Here's the second one, input 2. Then there's going to be a third one, and the fourth, and so on and so on. And for each one of these inputs, we carry out a full computation that starts in the initial state, goes to the final state, to the halting state, and once it's done, there's an output. So at the end of this first step that we call a macro step, here's the output. At the end of the second step, there will also be an output, and so on and so on and so on. Okay? So the inputs come in during the computation, the outputs go out during the computation too. Okay? So, but in addition to what I've just described, there's also persistence. Okay? And that's this intermediate, that's the second tape, the work tape. Okay? So it starts out empty, but at the end of the first computation, it's got something on it. And notice that at the beginning of the second computation, it still has that something on it. So the key here is that this tape, the contents of this tape, acts as the memory of the machine. Okay? It does not change from the end of one computation to the beginning of the next. Yes?
In a traditional Turing machine, there's a concept, I guess, of atomicity of operations. So you perform one operation, you're in a new state, there's new contents on the tape, and then you perform another operation. In this...
What do you mean by operation?
Some computation. The state moves, there's writing to the tape, the tape is changed. In this, is there any notion of atomicity of input? So is there a relationship between when the state changes and when the input comes in, or when there's writing? Do they happen
What
simultaneously?
you have described is what we call a microstep. It is a single step within a Turing machine computation where we read the current character on the tape, we look at the current state, we write a new character on the tape, we move to a new state, and we move the head right or left. Okay? So this all happens inside here, inside this computation. These individual, what we call microsteps. This here, we call it a macro step because we ignore the details inside. We are stepping back and looking at the bigger picture. Once this computation finishes and we're in the halting state, that's when this guy has some stuff on it. And this here, the red arrow, indicates magic. That's what we call the interaction step. That's when the observer of some kind replaces the input by the new input, reads off the output and blanks it out. But that observer never touches that work tape. The contents of that work tape is unobservable. And it's inside the machine. And so to go back and compare it to the Turing machine, standard Turing machine model, in the standard model, every computation, every new input is accompanied by zeroing out the whole machine. So the configuration of the machine must be exactly the same for every new input, except, of course, for the value of that input itself. And that's what we are violating here, because we are no longer starting each of these macro steps in the same configuration, because the work tape preserves its contents from the previous computation.
So one way, I guess, for me to understand this is you could think of a sequence of Turing machines, each of which, at the end of their computation, some observer looks at the tape, changes it somehow, and gives it back to the tape.
You can think of it as a sequence of Turing machine computations, but you're not dealing with the same Turing machine every time. By virtue of having different contents of the work tape, it is essentially, you need to think of it as a different machine. Okay? So let me move on. So here's what the computation looks like then. We've got this guy, which we call a persistent Turing machine. Here's his memory in the work tape. And he gets a stream of inputs from the environment, and he produces outputs, input, output, input, output. And together, these two together make up what we call an interaction stream. And the set of these interaction streams, of all the interaction streams for a given persistent Turing machine, is known as a persistent stream language. And this notion of persistent stream language is observation-based. We are only recording the inputs and the outputs. The contents of the memory is not recorded as part of the interaction streams because it's not observable. It's a hidden variable that is not part of the observable behavior of this machine. Okay? So, and we can define equivalence between these machines based on the persistent stream language, so we can say that two machines are equivalent if they have the same persistent stream languages. So notice that two machines can be equivalent when in fact inside the state of their memory at any point is very, very different, as long as the mapping back to the output ends up being the same. Yes?
It might be useful at this point to point out a connection that I think you were making this morning to me, that these are basically infinite state machines.
I will. That's later in the slide.
Okay.
Okay, first I wanted to give a couple of examples. So on the very next slide there, I start making it.
Okay, sure.
Okay? So one example is an answering machine. Okay? So an answering machine has three types of valid inputs, and I guess all the other inputs are assumed invalid: to record a message, to erase and play back. Okay? And the work tape of the PTM serves as the tape of the answering machine. So if you record a message X and Y is on the tape, it'll say OK as output, and now the tape will contain XY. If you say erase and there's X on the tape, then it'll return done, and the tape is now empty. If you say playback and X is on the tape, then it'll return X, and it'll still be on the tape. Okay? So the persistent stream language of this machine would contain a sequence as follows. Record hello, the guy says OK. Erase, he says done. Record John, he says OK. Record Hopkins, he says OK. Then you say play back, and he plays back John Hopkins. Okay? So this illustrates that sequential objects are modeled very conveniently with PTMs, where you use the work tape to store the internal data or the state of the sequential object, and you represent the method invocations of the object as inputs to that PTM. Another example, of course, is the driving agent. This also translates one-to-one into a PTM. Another example is the PowerPoint editor, okay, where the output at every point is the screen view, and your inputs continuously are cursor movements and key movements, and that ends up updating what you see. And of course, there are presumably other structures internal to the PowerPoint application that you don't see. Okay. So now I'm going to move on to one more example of PTM. And even though this example is more trivial than the others, it will allow me to introduce these animals, which are labeled transition system or infinite automata. Okay. So this example is that of a latch, where the output at every point is the first bit of the previous input, except for the first time around when you just output a 1. So you first output a 1, then you output the first bit of previous input, and so on and so on. Okay?
No matter
So-
what you input. No matter what you input.
Well, we're assuming that your input string sequences of bits, and you just output the first bit of the previous sequence, not the current sequence, the previous one. Okay? So there are three possible memory states, contents of work tape here. Originally it's empty, and then it's either 1 or 0, depending on what was the first bit of the previous string. So for example, at the beginning, if you start with an empty work tape and you see a sequence that starts with a 1, you will remember that 1 and you will output a 1. If you see a sequence that starts with a 0, you remember the 0, but you will still output a 1. Then from here, no matter what you see, you will output a 0. But if you see something that starts with a 1, you'll go up, and something that starts with a 0, you'll stay in this state. Okay? So this illustrates that these persistent Turing machines have a dual representation as labeled transition systems. In this case, there will be 3 states, 1 for each work tape contents. In general, of course, the number of states might be infinite. Same with the labels on these arrows. This is not a single label. This represents the family of all the labels for all strings that start with a 1. So in fact, there's infinitely many transitions in this picture. And if you follow this system, okay, so here we have a possible string here. So if you follow the system, you have 1, 1, then you have 0, 1, then you have 0, 0, and then you have 1, 0. So the streams in the persistent stream language of PTM correspond to sequences of labels on the edges of this transition system. Okay? So we call these systems interactive transition systems. And they're triple SMR, where S is the set of their states. Now note, these are not the states of Turing machines. They are the states of, they correspond to the memories of the persistent Turing machine. Okay. And so the set of them is not finite. And R is the initial state, and we assume that initially the work tape is always empty. And M is the transition relation, which is a quadruple. Original state S, input string, new state, and output string. And this guy is required to be recursively enumerable because these transition systems are the ones that are computed by the PTM, so for that they need to be computable.
So you just slipped non-determinism in, right?
The whole time we've been working non-deterministically.
Okay.
When I originally defined the Turing machine on which the PTM is based, I said it's not N3TM, that stood for non-deterministic Turing machine. But of course, deterministic systems are a special class, so the definitions in the paper, define that as a special subclass. So as I said, these interactive transition system can be viewed as a dual representation of PTMs. The class of ITMs corresponds to the class of ITMs, And the states of the ITS are the reachable PTM memories, meaning the ones that you can actually end up having as a result of some computation. And the labels of the ITS, this should be S, are the input-output pairs in your PTM computations. Okay? And you can define stream equivalence for interactive transition systems based on the interactive stream language, which is the set of all the sequences of labels. And this will be the same type of a definition, the equivalent to the definition of persistent stream language equivalence for PTMs. But you can also define other forms of equivalence. So I'm going to go through this very briefly. Not everybody here is a computer scientist. So one way to do it is to define isomorphism. So when two systems are isomorphic, that means that their sets of states are in a one-to-one correspondence. So it doesn't mean that they actually have the same memories, but it means that you can map the memories of two PTMs to each other. Or in the case of ITSs there, you can map their sets of nodes to each other, sets of states to each other, so that the input and output, WI and WO, are the same on the transitions in one and on the mapped transitions in the other. Okay? So this is a very fine notion of equivalence because it really expects a bijection between the two sets of states. And it turns out that there's a third notion.
How is the phi defined?
Phi is the bijection. Phi is the bijection between the sets of states. So if you look at any transition in the first guy, which has a current state, input, new state, output, this is the corresponding state in the other system, and this is the corresponding second state in the other system, but the label that goes from that state to that state will have the same input and output.
And presumably the phi is available in
No.
some other machine. I mean,
Here's an example. If you have an answering machine, one of them might encode everything in binary, the other in tertiary. So in fact, they don't have the same contents of the memory, but there's clearly mapping between them. Okay? Another example would be when the machine is supposed to act differently for odd messages rather than for even messages. So it might implement it with a counter, counting the messages, incrementing it one by one, or it might implement it with a binary flag, odd, even, odd, even. In that case, you don't have a bijection, and yet the behavior will still be the same if all that the machine cares about is whether it's odd or even. So in fact, that is not isomorphic, but it will be bisimilar. So bisimulation is a notion of equivalence that is very popular in concurrency theory. And up to now, concurrency theory, which all studies concurrent computation and it focuses on formalizing the communication within this computation, up to now it has had nothing to do with Turing machines. The two fields didn't talk to each other. So this is the first time that you're seeing concepts for one being imported into a model that is based in the other. Okay. So in bisimulation, the notion of equivalence is redefined recursively. We still have this pairing between states. This pairing is a relation R, but it's defined recursively that the roots are related with R, and two other nodes are related if for every child of the first one, there exists a corresponding child of the second one that's related, and vice versa. For every child of the second, there exists a related child of the first. So this is, if you have never seen bisimulation before, I don't expect you to understand it after this short introduction, but this recursive notion has great fixed point semantics. So if you take the fixed point of this definition, then you will get a relation over pairs of nodes from the two systems. And you say that they are bisimilar if this relation ends up being, onto and ends up covering all the nodes from both systems. Okay. So I already said that isomorphism is a much finer equivalence relation than ISL. Bisimulation falls somewhere in the middle. And furthermore, since these two worlds, the world of persistent Turing machines and the world of interactive transition systems, are duals of each other, okay, this notion correspond to each other, creating equivalent equivalence classes. Sorry for using the word equivalence twice. And the same thing here. You can define the notion of equivalence for PTMs that corresponds to the isomorphism. Here, it's harder to find a natural notion here, but due to the isomorphism, you can always translate a PTM. This notion ends up applying to PTMs because the two worlds are duals of each other. Okay. So why are we focusing on equivalence? Okay. We can think of equivalent machines as having the same behavior. Okay. So the notion of behavior is relative because there are different notions of equivalence. So relative to that notion of equivalence, their behavior is the same. Think of it as an observer observing the machine, and different observers have different observation powers, and some will find machines equivalent when the others won't, and that's why we have finer and finer notions of equivalent. So when we have equivalence classes of machines that are all equivalent to each other, the set of equivalence classes somehow corresponds to the set of distinct behaviors, and you can argue that if you have a finer set of equivalence classes, that means that the machines are capable of a larger set of behaviors, and this is how we're going to approach the issue of expressiveness, through the issue of equivalence. Okay? So we are not done with equivalence. Actually, we're only starting, because we're about to define an infinite number of equivalence relations all at once. Okay? So let L sub k of m be the set of prefixes of its streams, where these prefixes are of length k or less. So this represents finite observations of your PTM M. So you can only observe it for k interactions or less. And so what you observe during that time, that set of observations, is L sub k of m. You can also define this L sub infinity as the union for all the k of L sub k of m. So this is still a set of finite observations, but there's no bound on how large they are. Okay. So for these notions of equivalent, for these languages then, you get corresponding notion of equivalence. So two PTMs are equivalent sub k if they have the same prefix languages of length k or less. And they're equivalent sub infinity if they get the same prefix languages in an unbounded fashion. Okay. So here's an interesting example. Talking about observations. Suppose you have a deterministic Turing machine, and you observe its answer to the question, what's your name? Suppose it says, I'm Fred. Okay, from then on, you know what it's going to do every time that you ask it that question. You can ask that Turing machine once more, what's your name? It's going to say, I'm Fred. You can ask it 1,000 times, I'm Fred. 1,000,000 times, I'm Fred. Deterministic, you observe it once, you know what it's going to do. By contrast, a PTM can store on its persistent tape the number of times that you've asked this question. And you ask it 1,000 times, you ask it 1,000,000 times, and it will keep on saying, I'm Fred, just like the deterministic Turing machine. And then you ask it just one more time, and it'll suddenly say, I've told you 1,000,000 times, my name is Fred, I'm not going to tell it to you again. Yes?
I just feel compelled to point out that, I mean, why can't you have a Turing machine that does that? You can.
Dynamically generated inputs. Because every time you ask it, what's your name, it's a new computation.
You just make a string of 1,000,001.
Okay, consider then, in answer to your question, let's go back to the driving example and consider the inputs to there. Those inputs represent a video of what that car sees as it drives. If you pre-compute that video and give it to the car, then you don't need the car. Then you know exactly, then you've already driven. That's the only way to accurately pre-compute the complete video, including all the people that are going to be there.
But that has to do, that's a characteristic of the input, not the computational language.
But they are part of the computation now. We're no longer separating them. We're no longer thinking of computation as something that takes place outside inputs and outputs. Inputs and outputs are part of the computation. Yes?
So maybe one way to talk about what Charles is saying is that why don't we propose an oracle experiment where we have a Turing machine which is given an input and then also all the possible consequences of every output it chooses to generate. And then you could do exactly, this is equivalent to what you're proposing, whereas instead of the environment giving these dynamic inputs. We have an oracle giving these dynamic inputs. It seems like the only difference is for the Turing machine, you're setting a finite stop to the amount of data, whereas for the persistent Turing machines, you're saying there's an infinite amount of potential data that this machine can compute upon.
Yeah, it's infinitely extendable, but it's also, you see, since the next input is generated dynamically, and we do not make an assumption that the environment is computable, then there is non-computable dependence between earlier outputs and the new inputs.
Well, there's a theory of oracle computation in Turing machines, and in the oracle computation, you don't assume that the oracle is computable. You assume that the oracle is from somewhere. So it seems like this is Turing machine with an oracle.
You can also just forget it and say, well, you know, we can just break down the computation into sequence of individual computations, model it with a Turing machine, and forget it. I'm trying to provide a model that's actually useful. Because if you look at the way I modeled an answering machine, that was the complete description of an answering machine. Okay? It is prepared to deal with any sequence of people that come along, no matter how far apart, no matter what message they leave, it'll do the right thing. There's no need to resort to voodoo. There's no need for uncomputability. There's no need for oracles. Those are...
Now here in your example, the oracle implicitly is the environment. The voodoo comes in with this environment, which is doing some voodoo on the input.
But you see, I don't want to model the environment. I'm assuming the environment, I'm modeling the computing device, which interacts with the environment, but that device is an open system that functions within that environment. But you see, we're used to modeling closed systems. That's why you want to bring in that environment, put it in there and model it. At that point, everything is closed, everything is together, and we're back to the way things used to be. Okay? We're in a different paradigm. Okay? There is a stream heading out of our device. And we are modeling that device with that stream heading out to some place where we haven't modeled. And that's okay. So it turns out that these equivalence relations, observations of length 1, observations of length 2, sub 3, they partition the PTMs into progressively finer equivalence classes. So if you can observe for one more interaction, you will be able to distinguish more persistent Turing machines from each other than if you didn't. And the class of PTMs is broken up into finer and finer classes. So you get this infinite hierarchy, where at the bottom, you've got the observations of length 1. Here you have observations of unbounded length, though finite. And here you have persistent stream languages, and it turns out that there's a gap here in the hierarchy, which itself is an interesting result in the paper. Okay? So this here is the Turing machine equivalence, as I showed with my example of what's your name. You know, if you want to know about Turing machine, you only have to observe it for one step. Of course, you have to observe a whole bunch of different inputs, but only for one step at a time. Okay? So now that I've defined all these classes, I still need to somehow connect it to Turing machines and show that what we have is arguably more expressive. And the problem is, to connect it directly is impossible because Turing machines don't do streams. They only do individual pairs. So how do you compare head-on these two models which are seemingly incompatible? So what we do is we create a model that is halfway between them. So this model, which we call an amnesic PTM, it also has a stream of dynamically generated tokens. And it also computes a sequence of macro steps over the stream. Okay? So as such, it is at least as expressive as Turing machines, because each step here is a Turing machine computation. Okay? Then here it's another Turing machine computation. So it's at least as expressive as Turing machines, but these machines lack persistence. So unlike the general PTM model, not only do we replace the input at every step, and not only do we erase the output, but we also erase the work tape. So now it really is the same Turing machine at every computation, because except for the new input, the rest of the machine is the same at the beginning of every computation. We no longer have memory. So an example of this is a squaring machine, which at every point takes the input and just squares it and produces the output. It doesn't need any memory. So this is an example taken from the work by Prass and Ritkin, who used this as an argument who thought that our PTMs were amnesic and argued that they're less expressive, that they're not very interesting, that don't give you anything new. And we agree with them. It turns out that amnesic PTMs are not at all as interesting as the general case. Okay, there are two arguments that will lead you to that conclusion. The first one is that the infinite equivalence hierarchy completely collapses for these amnesic PTMs. If you only consider amnesic PTMs, then there's no infinite hierarchy at all. And what you can observe with one observation is as good as what you can observe with streams. The equivalence classes are the same. And another argument is if you look at the set of streams for amnesic PTMs, they are a strict subset of the set of streams for persistent PTMs. So, given that you accept our notion of expressiveness in terms of equivalence, okay, it is clear that amnesic PTMs are less expressive than the general case, and yet they are at least as expressive as Turing machines because they represent a sequence of Turing machine computations. Okay? So we summarize everything we've shown up to now. The equivalence hierarchy of the three equivalences of systems. This is the equivalence for amnesic stream languages. And this is the two classes. Any questions? Okay, so what I've been describing, the kind of computations that PTMs perform, we've called them sequential interactive computations. Okay, so in sequential interactive computations, the system continuously interacts with its environment by alternately accepting an input string and computing a corresponding output string. And there are lots of examples of computation that we already know in our everyday life as computer scientists that are all sequential interactive. Okay? All right. So now we will present a thesis. It is in the paper. The paper is available right here, some reprints. It was published in Information Computation. The thesis is that whenever there's an effective method for performing sequential interactive computation, this computation can be performed by a persistent Turing machine. Okay? Now, as any good thesis, it is something that equates a formal notion with an informal notion, so you can't really prove it. But the way you make this argument more convincing is by describing the way you would simulate any sequential interactive computation with a persistent Turing machine. So simulation is an important concept in such thesis. So what we have defined is a universal persistent Turing machine which simulates any other persistent Turing machine. And all it needs is one additional input that takes place at the very beginning of the computation that describes the PTM that is to be simulated. And we give that description to the universal PTM once at the very beginning, and from then on, it will behave exactly like the PTM that it's simulating. So here's an example of a universal PTM simulating an answering machine. The first input will say simulate AM, where AM is the actual description of this PTM. And it'll say, OK, I'll do that. And from then on, the rest of it is exactly what we've seen before. Okay, the details of how to do this are in the paper. And it's also pretty clear that you can, in an analogous fashion, simulate any other sequential interactive system, such as any of the ones described in the examples on the previous page. Okay? And that is what led us to our sequential interaction thesis. Okay? Any questions?
Could you go through this example? I don't know what it means actually, all right? I mean,
okay, the
red stuff is
the red stuff is inputs, the blue stuff is outputs.
Yes.
So this here, if you ignore the first line,
simulate is a command, is that right?
This here is input, just like the other inputs. Okay? This input is also finite length, just like all the other inputs. What this input says is that here's the description of the machine that I want you to simulate. And the machine, of course, is finitely describable. So it says, here's the description of the machine that I want you to simulate. And you say, okay. And from then on, the description of that machine stays in the memory. And so is the current state that that machine is supposedly in. And so from then on, it can simulate the persistent stream of that machine as if it were that machine. So if you were to yank out this first, the head of the stream, the tail of the stream actually is exactly what the answering machine computation would look like. Yes?
In music, Turing machines are just an infinite sequence of regular Turing machines.
Yes, exactly. Of the same computation, the same Turing machine every time.
So what prevents you from making the sequential input dependent on the previous work tape?
You have to observe the work tape. It's not observable. If you
Isn't
make
that
the
part of the
non-observable
environment,
observable, huh?
But isn't that what you're saying is part of the environment?
No, the memory of a PTM is deep inside it. It's not observable. Okay. This is like the Schrodinger cat. You observe it and you change the notion of equivalence. Not Schrodinger. Is it Schrodinger cat that you can't observe? Okay. All right. So now we will follow up with a question that is natural for computer scientists. It may not be natural for engineers, but for computer science, it's natural. You say, aren't you doing something wrong here? Aren't you violating the Church-Turing thesis? Isn't somehow what you're saying heretical? So to answer that question, which is a natural question, let's revisit the Church-Turing thesis. The Church-Turing thesis says whenever there's an effective method for obtaining the values of a mathematical function, that function can be computed by a Turing machine. Okay? So now we need to contrast it with a common reinterpretation of it that we call the strong Church-Turing thesis. So the strong Church-Turing thesis, which is the way we usually understand the Church-Turing thesis, says a Turing machine can do or compute anything that a computer can do. Essentially, all computation is it can be done by Turing machines. Okay? Now note that the two are not the same. This only talks about computing mathematical functions. It does not claim that mathematical functions are all computation. Okay? And in fact, the equivalence of these two interpretations of the original thesis and its interpretation, that equivalence is a myth. Okay? We just saw that the function-based behavior of all algorithms does not capture all forms of computation. It does not capture control systems. It does not capture driving home from work. It does not capture word processors, operating systems. Even it doesn't even capture sequential objects. But the myth that these two things say the same thing, and that this one has the same validity as the original, has been dogmatically accepted by the computer science community. Now, before I go on to discuss why this happened, I would like to point out that in my view, Turing would have been against this version of the thesis. He would have said, I disagree with it. In the same paper in 1936, where he introduced what we now call the Turing machine, he also introduced what he called choice machine as a distinct model of computation. And the choice machines extended Turing machines to interaction by allowing a human operator, by stopping once in a while and allowing the human operator to make choices during the computation. Okay? So they interacted with the operator. And he presented it as an alternative notion of computation to that of Turing machines, and he never claimed that Turing machines formalize this kind of computation. Okay? So now we will go and look at the origins of this myth. Why is it so powerful, and if it's wrong? Okay? So basically, we can deconstruct that myth into three separate claims, where each claim is in fact correct, provided that you understand the assumptions behind it. And the problem is that when you forget the underlying assumptions and allow yourself to combine them, what you then get is the incorrect conclusion. That Turing machines equals solvable problems, equals algorithms, equals computation. Okay? So let's look at the first part of it. Turing machines equal solvable problems. The assumptions, of course, here is that all computable problems must be function-based, because that's what Turing machines do. They do functions. Okay? That assumption is there for a reason. The reason is, as I mentioned before, that theory of computation started as a field of mathematics. And mathematical principles were adopted for the fundamental notions of computations. In particular, they identified computability with the computation of functions as well as with Turing machines. Okay? And it is also important to point out that, you know, if you look at the way early computers actually computed, you know, it would take a big leap of imagination to conceptualize computation in any other way but the way it was originally done. Because the batch mode, modus operandi of original computers, in fact, did represent function-based computation at that point. The second part of the Church-Turing thesis myth is that solvable problems equals algorithms. Okay? And this assumes that algorithmic computation is also function-based, i.e. that the role of an algorithm, its job, is to transform input data to output data, finite amount of data here, finite amount of data there, finite amount of time in between, everything closed system, just as we had in the original, on the first slide in our talk. Okay? And again, this is not accidental, this assumption was made. And the original is that the word algorithm was not invented by computer scientists. The word algorithm existed in the mathematics long before that, and the original meaning of the word algorithm was precisely function-based meaning, such as Euclid's greatest common divisor algorithm. And if you look at Knuth's textbook on algorithms, which was the Bible of algorithms, he actually devotes a couple of pages to just discussing what is an algorithm. And in his discussion, he's very careful to, in fact, define this notion in a way that is function-based. So, for example, he makes sure to point out that algorithms are given to the inputs are given to the algorithm before the computation begins. He also says the computation is closed form, and all the standard assumptions are there in Knuth's paper. So when he then says we will equate algorithms with Turing machines, he's right. That notion of algorithm is perfectly equivalent to a Turing machine. What happened then is, what ruined everything is this equivalence here. This equivalence is again for a reason, and the reason was the ACM. In the 1960s, computer science programs started popping up all over the country. And the ACM said, well, we must provide a common curriculum for all these programs, and for that we need to define what exactly is and is not computer science. And so in 1968 they put out this big report where they adopted algorithms as the central concept in computer science. So the idea was to give legitimacy to this new field on par with the kind of legitimacy that physics gains from the concept of energy. So the only problem was they did not explicitly agree on just what an algorithm is. Okay? So whereas Knuth was very careful in his definition of an algorithm, thereby in fact defining something that's equivalent to Turing machines, other textbooks were much less careful. Typically, these textbooks were not theory textbooks, but were programming textbooks that nevertheless chose to put things in terms of algorithms because that's what the ACM prescribed. So an example is a Rice and Rice textbook, which defined algorithms as follows. An algorithm is a recipe, a set of instructions or specifications of a process for doing something. That something is usually solving a problem of some sort. You read this, okay? And if you're an undergraduate without any background on this topic, you would have no idea that this describes function-based computation. But yet, students learned that somehow this is equivalent to Turing machine computation. And by now, we are so used to describing an algorithm this way and leaving out all the explicit descriptions that Knuth originally had that justify its function-based nature, that Sipster's description in the contemporary theory textbook sounds an awful lot like Rice's. An algorithm is a collection of simple instructions for carrying out some task. Commonplace in everyday life, algorithms sometimes are called procedures or recipes. You'd swear that he's describing an interactive process. And yet he also says these are equated to Turing machines. And that And so this equivalence of algorithm computation and then muddying the definition of an algorithm to in fact match our notion of computation now in fact describes a different animal that is no longer Turing equivalent. Okay? So I wanted to point out something that came up in discussions today, that that the decision of the ACM and of computer scientists to define their field in this way, in terms of algorithms and in terms of Turing machine computation, ended up automatically classifying a lot of emergent topics into whether or not they were part of computer science. So information theory is one of the topics that, and control systems are another topic that ended up not becoming a part of computer science because they did not fit this algorithmic model. So some of the distinctions that we have between what is and is not computer science versus electrical engineering go back directly, in my view, to this decision, which actually was, it was not really made by the ACM. The ACM curriculum reflected the spirit of the leading computer scientists, and it was the community that ended up predominating, the group that ended up predominating in the community that made these decisions that thereby relegated control systems and information theory to their non-computer science status. And I'm glad that this center is merging them back in, because they've always been very important for the computation, even though they force us to rethink exactly what is computation, and as well we should. Okay? So, again, what I'm not claiming to redefine, to actually tell people to compute differently. Computation has been shifting to the interactive paradigm, for a while now. Some fields have shifted more than others. So in AI, it's been a while since logic and search has been replaced by more interactive approaches. In programming also, we have our systems that are all component-based and object-oriented. And we are now more and more looking at the phenomenon of emergent behavior. And so computation is all moving in this direction. I'm just providing the impetus for the theory of computation to catch up with the rest of it. Okay, I don't have the time. So, in fact, ours is not the only model of interactive computation. There have been many other interactive models. Reactive and embedded systems, interaction games, online algorithms. There have even been other Turing machine extensions. Okay, in fact, there's this whole other field I mentioned before called concurrency theory, which focuses on communication between concurrent processes and tries to formalize it. And Milner got a Turing Award for it, I believe. But all along, that work has positioned itself as orthogonal to the theory of computation, because the myth of the Turing thesis is so strong that you did not want to challenge it until very recently, when it became clear just that interaction that is predominant throughout computer science. So what makes PTMs unique then is the fact that it's the first time that we've actually gotten a result that you can argue shows the greater expressiveness of interaction over Turing machines. And not only that, but it's the first approach that actually gives promise of bridging concurrency theory and traditional theory of computation, which so far, up to now, have been speaking different languages and not intersecting at all. And so I'll conclude with the 3 conjectures that I currently have that it would be nice to prove. The first is that within sequential interaction, one can develop notions analogous to the notions within Turing machine computation for computational complexity, for logic, and for recursive functions. So analogous notions can be defined here as well. Another conjecture is that multi-stream interaction, where you have multiple agents and multiple autonomous strings at once, is even more powerful than sequential interaction. This is actually Peter Wegner's conjecture. So I have not captured that notion of interaction. I've only captured sequential. And the last one also has to do with indirect interaction, where agents interact via their environment rather than directly via message passing. And I have a conjecture that direct interaction, which is the kind of interaction captured by concurrency theory, is not sufficient by itself to capture all forms of multi-agent behavior, and that it is also necessary to have indirect interaction. Okay? And this talk is based on these 4 papers, which are all on my website. And this particular paper, the one with all the hard proofs, is available here. I brought some reprints with me for those interested. And thank you very much for coming. Yes?
So, can you go back a slide to your conjectures?
Right there.
Right, so it seems to me that these are the right kinds of questions to ask, and I also was thinking about other ways of maybe enriching the model. You have this model where the user, where the machine and the environment take very polite turns with one another. So there's no notion of interrupts, or parallelism, or in-queuing requests. Would those change the power of the formalism?
I believe...
I mean, even your notion of equivalence assumes that the 2 machines can't be equivalent unless the dialogue takes the same number of turns in both.
On the other hand, if you think of if you think of this as discussion, as I have this on here, basically we've moved from answering questions to holding discussions. So you're saying we've got a polite discussion, but in fact, even if people interrupt each other, provided they don't talk at exactly the same time, provided, it's still taking turns. It's just the reason for your gilding your turn is different. So in principle, I think that it would be equivalent.
Well, so the reason I thought it might not be is that the environment might be able to interrupt a computation that wouldn't otherwise halt.
Oh, a non-halting computation gets interrupted by the environment. That's an interesting one. In the paper, there's a lot more in this issue of halting than I presented in the talk. So we have defined this subclass called decidable PTMs, which are guaranteed to hold for all reachable memories. And so I believe that any sequential computation, when a computation, if your computation is sequentially interacted, then it should be doable by a decidable PTM. And but so once you have a decidability, then you always halt. So it's divergence is no longer possible. Okay, so I'm still skeptical that you actually get anything new, but we can talk about it offline.
And I guess the other thing to, if you want to play around with extensions to this to see what adds power, you could also drop the notion of sequentiality. So you could imagine that a computation consists of, it's in a circle, and the work tape at the end of computation n has to be the same as the work tape at the start of the first computation. You can imagine things communicating in all kinds of grids and other
in AI, this is notion is episodic computation, where you keep on going for a while, but eventually you end up coming back to somehow to not necessarily to the initial state. After, so for example, a chess game, you take turns, everybody produces their input, but at the end, once the game is over, then you revert. So it's.
I don't think this one adds any power, by the way. It just means that the halting
Actually, the
condition is
question
that
is
you have to
whether
be
it
equivalent
reduces
to your
power.
original state.
The question is whether it reduces power, and in fact it does. Because if you're guaranteed to have, then it becomes equivalent to L sub k, where k is the length of the episode. So at that point, you don't have the infinite hierarchy of expressiveness.
Okay, I didn't follow that, but we can take it offline.
Okay.
Well, can I ask, how is it possible that the working memory is inaccessible?
In the computer, the memory is always readable. I can look there.
Well, I usually prefer actually to think of intelligent agents. Maybe, think of it as the mind of the machine. You can ask it what it's thinking, but an intelligent machine in principle doesn't actually have to tell you everything that it's thinking. So whatever it tells you, you can say that two machines are equivalent if they tell you the same thing. But in fact, you never know if they really do have the same thing on their mind. And maybe one of them is totally crazy, but he's decided that he's going to fool everybody by making people think that he's sane. But as long as he actually acts sane, you would never know that he feels that way. Until he actually does something crazy, you would never know that he thinks that he believes himself to be crazy and that he's just fooling everybody into thinking he's sane. It's the hidden variables is, it's very important for the model to have it hidden, because also in the context of resource boundedness, for example, imagine a machine whose inputs are binary. But inside, in memory, you have a huge thing like maybe a neural network or a decision tree you've built up. And if you were to see this, then, and you say they're equivalent, that would mean that you're no longer having binary inputs and outputs. Then all of a sudden, your inputs and outputs have to include this long description. So even though it's hard to explain, but the notion of, you've just destroyed the notion of equivalence. It's, you're no longer allowed the machines to think differently and act the same, and it's somehow you've destroyed what makes them more intelligent and more expressive. I'm sorry I can't say it better, but it's also the fact that if you're forcing the human being to see what's in the to work with the memory directly, you're allowing them to corrupt it, and therefore the set of computations can't possibly be the same, because you can't force the observer to treat the memory as gingerly as he ought to. You just can't force that. Yes?
So on one of your slides you showed the old paradigm and the new paradigm. And in the old paradigm was procedural programming, and in the new paradigm was, was object-oriented programming. And that confused me, because a number of times during this talk you've talked about things in the new paradigm which have been programmed using procedure-oriented programming. And some examples are OSs, which are most of the time done in procedural programming. You introduced a function, which was a static C function.
By procedural programming, we mean pure procedural programming, where there are no global variables, there's no side effects. In OSs, you have these queues which live, and you have processes which interact with them. But it is a pure procedural, is the kind of stuff that you can formalize nicely, with lambda calculus. And as I said, no side effects, no go-tos, random go-tos, no global variables.
You mean functional programming?
Huh?
You mean functional programming?
Well, no, I was just thinking of a pure procedure. We can think of your program as basically being a procedure. Takes the input, produces output, and all the subroutines, you have them separately for convenience, but you could just roll them into one program. So the whole thing is just one computation from input to output. That's what I meant by procedural.
Well, can't you say the same thing? Well,
It's by object-oriented programming means that it's a question of it's possible that if you take all the objects together, again, you form a closed system, at which point it is equivalent to procedural programming, okay? But we're now looking at capturing the behavior of objects not without having to close them. Whereas in procedures, every time you have a procedure, it forms this nice transformation of its input to its output. It is not an open system within itself. But every every open system, if you close it, it's no longer open. So there's no compositionality.
Well, I think.
Okay.